Um, I've played a lot of video games in my life, and one day after I took a calculus class, or a little bit after I took a calculus class, I wondered if I could describe the battle mathematically. And I thought about it for a few minutes, and these differential equations here are what I came up with. Basically, the assumption is that the bigger the army is, the faster it can kill the other army. So X and Y are the size of armies here, and T is time, obviously, and B and C are constants describing how well they fight. So if B is bigger, it means the Y army can kill the X army faster. So these are differential equations, and there's a solution to the differential equation, obviously. It's right here. Oh, I forgot to show you actually the most useful part. Oh, wait a second. I actually wrote a book about similar subjects, and that's what this is. No one's read it, actually, but, except for me. I'm just going to show you this part now, though. Okay, so you can get a solution in terms of X and Y that neglects time, and this is a hyperbola, or actually the Pythagorean theorem, depending on how you set the equation up. Well, I'll show you. It's either the Pythagorean theorem or a hyperbola, depending on what you do with it. Anyway, this is the size of the Y army, and the size of the X army, and the size of the Y army at the end of the battle. So you can use this equation very simply to calculate the size of the armies. If you know the size of the armies at the start of the battle, you can use this equation very easily to find the size of the winning army after the battle is over, assuming a perfect mathematical case that fits this definition. And for simplicity, I set B and C equal to 0, although that's not necessary. You can keep them there and they'll show up in this equation. I think B probably shows up here and C probably shows up there, I don't remember. So this is the solution without time, and this is the solution with time. It's quite a bit more complicated. You can see these are exponential graphs. Probably this won't make any sense just looking at the equation, so I'll actually show you a chart in a second. Anyway, and I also calculated how long it takes for the losing army to be completely destroyed. That's what this is. You can see it's proportional to the natural logarithm of the size of the armies. I thought that's interesting. That means if you make the armies like 1,000 times bigger, that'll roughly increase the time of the battle only by a factor of 3, roughly. I guess natural logarithm is a bit different than log 10, but I don't remember. And if you do this math, you'll find several conclusions you can draw. It takes actually a bit more math to prove this stuff, but I'll just read you what I concluded after doing the math. I concluded that power struggles fitting this initial assumption, this differential equation, they are inherently unstable, and therefore in any battle of this type, small advantages become large with the passing of time. So because of that, if you're winning, you should keep pushing really hard and not let up, and if you're losing, you should try to run away or avoid fighting, if possible. And I think if that weren't the case, then probably no one would fight wars, because it means the winner proportionately loses a lot less than the loser. If you fought a war and both sides lost the same amount of stuff, then it seems like there wouldn't really be a winner or a loser. Both sides would always lose. So I think there probably wouldn't be wars unless at least one side expected to win. You should never split your army into pieces if it can be helped. That effectively makes your army smaller. The most crucial part of the battle is where it's most certain. That means if there's a battle that's sort of spread out, I did some math that modeled it. There's like several battles taking place at once, and I showed that adding reinforcements to a battle, an extra reinforcement is most useful in a battle that is very uneven. It doesn't do as much if the battle is fairly well decided. And I also tried a separate differential equation that assumed that the casualty rate was also proportional to the size of your own army, which I modeled as meaning like it's sort of a guerrilla warfare where people sort of encounter each other randomly. And I found if I did that, I got a slightly different result. Strangely, this equation holds true in a lot of different situations, including this one. But instead of the battle being over quickly, it sort of drags out forever. I'm not going to show you that though. So I'll show you the chart I made. I made an example battle where the size of the Y army, which wins, is equal to 1 at the beginning of the battle. You could treat it as like 1,000,000 or 1,000 or something. It doesn't really matter. And the X army is half as big. And when you plot it, the X army versus the Y army, the battle starts out here, and with time it sort of moves like this. So it's a hyperbola, like I told you. This is the graph with respect to time. The Y army starts out with 1 and eventually goes down to 85, I believe. And the X army goes down almost in a straight line to 0. And this is a good demonstration of the point I made that the winning army proportionately loses a lot less men. Both armies here are equally skilled. It's just the bigger army has more troops, so it loses only 15 troops, and the losing army actually loses 50. Now, actually, the quality of the troops on both sides is the same, like I said. The reason this happens is that there's such a big difference between winning and losing is when you kill an enemy troop, it prevents that troop from fighting back, from shooting back at you. So you effectively killing an enemy is roughly equivalent to adding an extra troop to your side. And since the bigger army is bigger, obviously, it can kill more stuff. It kills the opposing army faster, and that prevents the opposing army from shooting back. And that's why it might not be how you expect. You might expect that if the troops are if two armies are equally skilled and equally well supplied and all that, you might expect that both armies, that they'd perform about equally well, but it turns out it looks like the size of the army is actually more important than the skill. And I actually tested this in a video game. I'll show you an example after I'm done recording this segment. I play Age of Empires, or at least I used to, and I made custom maps where I had a block of 100 units fire at a block of units of different sizes. I don't know what I just clicked on. So in the tests I did, I had a block of 100 units, and I did 4 different battles, and in the different battles they fought against an army of 30 units, an army of 50 units, an army of 60 units, and an army of 80 units. And at the end of the battle, I counted how many were remaining in the larger army, and I did the experiment and I wrote down the results, and these are the results. And according to the math, this is what was expected. So you can see they fit pretty well. I graphed them, and you can see basically the experiment and the math, pretty much they overlap. And I think the reason there's a bit of discrepancy is that the video game has discrete units. It has like 100 units, whereas calculus is continuous. I think if the game were somehow made continuous, then there would be no discrepancy. But yeah. So I'll end this video and I'll show you an example of a battle I did. In the battle you'll see a block of 100 units fighting a block of 50 units, and you'll see at the end of the battle that 85 units are remaining in the larger army, like what it shows in this graph. And the math would expect 87, or actually 86.6, but you can round it to 87. So it's pretty close. I think it shows the math is